Okay, in this assignment, we're going to be looking at forces and acceleration and how they relate to mass. There's a kind of classic equation that relates force, mass, and acceleration. That is F equals ma, force equals mass times acceleration. We can also rearrange this equation, so if we don't have a mass and acceleration to just plug in to solve for force, we could say plug in force and mass and solve for acceleration. Or we could plug in force and acceleration and solve for mass. Mass is the easiest thing to measure in the lab, so when we're using this equation, usually mass is something that we will have on hand. We'll be able to kind of either figure out the mass by measuring it on a scale or something like that. And there are some masses that will even tell you the mass of the weight on it directly, like it's calibrated to be that. This is like a 50-gram mass, or this is a 1,000-gram mass. So that's usually pretty easy to get to. Mass is going to be in kilograms in this case. And I think all the masses on this assignment are already in kilograms, so we don't have to convert it. But in the lab, you might have to. Force is the next easiest thing to measure because we can use force scales or spring scales that will tell us a force in newtons as a spring is stretched from the weight of something being pulled down by gravity, or as something is being pulled along a surface, or as it's being pushed along a surface. The scale will tell us, based on the compression and the expansion of that spring, how much force in newtons, big N, is being applied there. So acceleration is by far the hardest thing to measure directly in the lab, and so a lot of times it's what we end up solving for. But different situations might require different ways we set up the equation. So we're going to be looking at a couple different ways we can arrange the equation. This force triangle here is one of the ways we can do that. So if you imagine covering up one of these variables, either the F or the M or the A, what's left is what we are going to be using and calculating with. So let me see if I can okay, yeah, so I'm going to kind of cover up some of this. All right, so let's say that we wanted to solve for force. We want to figure out and calculate what force is. So if I go and cover up the F, kind of take that out there. Okay, and take out these two equation symbols here. Go with it. What's left is this M times A. Okay, so force is going to be equal to the mass times the acceleration of whatever object is in motion, whatever is accelerating. Okay. But like I said, a lot of times acceleration is the hardest thing to actually directly measure. So a lot of times that's what we want to solve for. So let's say we're going to solve for acceleration. So I'm going to white it out. Okay. I'm going to block out these two math operations next to it. All right, so what we have left is force divided by mass. If we take force divided by mass, we should get the acceleration. I want to point out that you can also get this equation by rearranging it algebraically, but since this isn't a math class, it's a science class, I try and take the focus off of the math part a little bit so we can focus in on the physics part of it. So if you are familiar with algebra, you could also just take F equals M times A and rearrange it with algebra, divide both sides by mass, and you'll get this same equation. You'll get F divided by M equals A. But a lot of people, I think, find that they're not huge on algebra, and so I think it's more important just to focus on using the equation and knowing how to plug it in and stuff like that. So this is what we end up with. So acceleration would be equal to force divided by mass. Okay. And finally, this isn't a very common situation, but maybe, just maybe, you don't know what the mass of the object is. So we are going to solve for it. Okay, so we're going to cover up our M. There we go, and the math operations that are going with it. So what we have left is force divided by acceleration. Okay, so mass would be equal to the force divided by the acceleration. Okay. Now, aside from this force triangle method, I also usually will include just the different versions of the equations already rearranged, so that way, you can get right to it if need be. Okay, let's switch back to the mouse. I'm going to that toolbar now. Okay, so on this assignment, you're going to have 3 attempts, so you can always go back and fix some stuff if you missed something. Let's take a look at some examples. Okay, so on the first page, we're just going to rearrange the different equations. So kind of what we just talked about. So force equals what? Well, again, if you go and cover up the force here and these two operations that are with it, what we're left with is mass times acceleration. So let me bring this back here. Whoops. There we go. So force would be equal to mass times acceleration. Oops. Oh, I gotta go back. There we go. Oh, and it moves my... Okay, so I guess I can't do the annotations at the same time. It's unfortunate. Okay. So force is going to be equal to mass times acceleration. Okay. If we want to look for what mass is equal to, we cover up mass, and what we're left with is force divided by acceleration. Then acceleration should be force divided by mass. Okay, so these are the 3 different kind of versions of the equation we can get by rearranging these variables. F equals m times a, m equals f divided by a, and a equals f divided by m. Now let's take a look at the next problem. Okay, so we have 2 balloons flying around, and they're flying with the same force, 0.02 newtons. So let's see. Okay, so the mass and the acceleration of each balloon affect the force, and we've got the original force equation here. If one balloon has a higher mass, or is heavier, it will have a blank acceleration, either higher or lower. So it's going to speed up faster, or it's going to speed up slower than the other balloon. In other words, it will speed up blank, and slower or faster than the other balloon. Okay, and this is talking about kind of in the perspective of the lighter balloon, the lower mass balloon. Will it accelerate faster or slower than the other one? Same kind of thing. So let's think about this. Both balloons are going to have a force of 0.02 newtons. So let's get the pen out here. So our force is going to be equal to 0.02 newtons. And that should also be equal to mass times acceleration. Or I guess I used... I think I did mass in blue. There we go. Mass times acceleration. Something like that. Okay, so let's imagine this for the bigger balloon. So if my force has to come out to be 0.02 newtons, and my mass is bigger, so still getting used to moving around on this menu. So let's say we got a really big mass, okay, like a really large number. I'm going to make that a really big M. Okay, that means to get the same force, if I'm multiplying now a bigger number to something and getting the same answer, my acceleration is going to have to be smaller. Okay, so to get the same force, a big mass is going to be applied to a very small acceleration. Now, if I go the other direction, and I have the force for the light balloon equals 0.02 newtons, that's going to be equal to a very, very tiny mass, very, very light balloon, times acceleration. I want that to come out to still be 0.02 newtons. If my mass is really, really small, I'm going to need a really, really big acceleration. Okay, so if I should be getting the same answer here, if one of these goes down, the other one has to go up to make up for it. Okay, a smaller mass is going to mean a higher acceleration. Okay, and a bigger mass is going to mean a whoops. A bigger mass is going to mean a lower acceleration. This is something that we observe with inertia. If you have a big, heavy object, it's hard to get it moving faster and faster. Okay, so if we are applying the same force to it, it's not going to be accelerating as much as a light object, which is very easy to get moving. It has less inertia. So a heavier balloon, is going to have a lower acceleration, which means it's going to speed up slower than the lighter balloon. The lighter balloon is going to have a higher acceleration. It's going to get going faster and faster compared to the heavier balloon. Okay, so whether you work that out with kind of the math or just by knowing inertia, I think it gets easier if you think about real situations. Like instead of balloons, try imagining getting a bowling ball moving compared to a marble. One of those is really easy to get really moving really fast. If you imagine just like whipping a marble across a hallway, if you compare that to a bowling ball, you got to really give it some oomph to really get it moving. Okay. So let's look at some more examples. Clear the screen here. Starting to get the hang of that. Okay, speaking of bowling balls, okay, assume that a bowling ball with a mass of 5.44 kilograms accelerates at a rate of 2.00 meters per second squared. What is the force on the bowling ball? So in this case, we actually have numbers, and we're going to plug some stuff in to calculate an answer. We want to figure out the force, so we want force equals to something. So whether you use the force triangle down here to get that equation, or you just pick out the right one that's got force listed right there for you, I'd say this option looks best. Force equals mass times acceleration. Let's see if I can highlight it. That guy right there. Okay, so let's get our calculator and plug this in. Let's see if I can squeeze it in here somewhere. Okay. So if our force is equal to mass times acceleration, our mass is 5.44 kilograms times our acceleration, which is 2.00 meters per second squared. So 2.00, I hit equals, which I think is this down here. There we go, yeah, 10.88 is our answer. So the force on this bowling ball is 10.88, and force is measured in newtons. So let's go down here. Make sure that's one of the answers. Hey, it is. Our force is 10.88 newtons. Let's do another example. Let's go to the next one. Okay, still working with that bowling ball. So in this case, our bowling ball is the same mass. It's still 5.44 kilograms. It didn't suddenly shrink or get bigger or something like that. But now we have a frictional force fighting back against the bowling ball. So this is not the force that we're applying to get the bowling ball moving. This is the force that's fighting against the bowling ball moving. It's what's slowing it down. It's from the deceleration. But we're still thinking of this as how fast or slow it's changing its speed. So whether we call it acceleration or deceleration, we're still talking about the same thing. It's really just acceleration in the opposite direction of where it's moving. So if our bowling ball is moving forward, then this just means that our bowling ball is going to be kind of giving a force in the backwards direction to slow it down. Okay, so what we're really solving for here is acceleration. We're going to plug in that mass that's still 5.44 kilograms and this frictional force of 0.392 newtons. And we're going to figure out what the acceleration is from there. So again, whether you just pick out the equation that has A equals, if you recognize that, or if you go and find an equation that you cover up the missing thing in your force triangle and see how your two variables that you have numbers for get multiplied or divided. we can get those. So let's grab our calculator, clear that out. Okay, so in this case, we have acceleration is force divided by mass. Okay, that F over m, that kind of fraction looking thing, is the same thing as dividing by something. So force divided by mass is what we're going to do here. So our force is 0.392 divided by the mass of the bowling ball, which is 5.44 kilograms, equals, we get about 0.072. Okay, and that should be our acceleration on the bowling ball to slow it down, how much it's slowing down by the rate it's slowing down. So 0.072. Let's make sure that's one of the answers down here. Hey, it is. It's a good sign. Okay, so that's how, it's kind of the rate of how much the friction is slowing down our bowling ball as it's rolling. Let's look at one more of these. Okay. The bowling ball applies a force on the pins when it collides with them. So it reaches all the way down to the end of the lane, whacks the pins. It applies a force of 9.50 newtons to one of those pins, and that pin accelerates when something has a force acting on it, whether it's in the direction of motion or against it, or it's on a standing still object. That object is going to accelerate. It's going to speed up or slow down. It's going to change its motion. So in this case, we're going to figure out the mass of the pin based on how much it accelerates by and how much force we put on it to get it to accelerate that much. Okay, so in this case, since we're looking for the mass of the pin, well, we want m equals some other stuff. So let's use this equation here. Blue, all right. So let's grab our calculator. And I'm actually thinking, can we, okay, never mind. Okay, so if we take the force and then divide it by the acceleration, remember this fraction bar basically just means the same as dividing. It's top divided by the bottom, numerator divided by the denominator. So our force is 9.50 divided by 5.98. What we get is 1.5886 and a whole bunch of stuff. We can round that to somewhere around 1.59 or so. So let's see if that matches up with something down here. Ooh, right there, 1.59. And our mass is in kilograms. Okay, so whether you're trying to solve for force or mass or acceleration, it's just a matter of picking the right equation. Let's see what these other questions are like. Okay, so this is one where you're calculating the force again. So you're picking the equation where you can have F equals and solving out for it. Okay, question 7 has us plugging in a force and a mass to find the acceleration. Okay, so again, just plugging it in, making sure you have the right equation. Okay, the last page has some calculation stuff, and it's also some thinking stuff. So let's see. We have a baseball flying through the air. It's falling with a force of 1.42 newtons and accelerating at a rate of 10.0 meters per second squared. Okay, so first we're going to solve for the mass of the baseball. And then it's going to ask us some other questions about how that would affect the force if we had other stuff going on. So if there's more air resistance, but the mass was the same, and it lowered the acceleration, that force pulling towards the ground would be what, more or less? Let's see. And then if we used a heavier ball, so the mass was bigger, how would that affect the force? Okay, so these are kind of thinking questions. If you're ever stuck on something like this, you might try just throwing in some random numbers. So we have here that the ball has a force of 1.42 newtons and a rate of 10 meters per second squared. This part of the question is asking, hey, if we had a lower acceleration, what would that do to the force? Would it be greater or stronger than 1.42 newtons, or would it be weaker than 1.42 newtons pulling on it? So maybe you go and plug in an acceleration that is less than 10.0. Maybe it's like 8.0 or 5.0, and test out what happens to your answer when you use the mass of the baseball you figured out here, and that lower acceleration. Does your force come out to be bigger or smaller than 1.42 newtons? Okay. In this case, let's see, we've got acceleration is the same. Okay, but we have a heavier mass, so maybe instead of the mass you calculate here, you plug in a bigger number and see how the force comes out. So you can also do this kind of conceptually. You don't need to do this just with numbers and doing calculations with sample values. But whichever way works better for you, it should work the same way. So either think about it conceptually, think about what it would mean if the ball is accelerating less. What would that do to the force? Or if the ball was heavier, what would that do to the force? You can think of it in extremes, like what if it was like a bowling ball dropping instead of a baseball? Would the force be bigger or smaller on that? That sometimes helps me to take really extreme situations and imagine that. Okay, so just a couple more thinking questions to finish off the assignment.